All right, hello again, everybody. Welcome back to Math Background for Machine Learning. So today we're going to continue with probability. So let's, I guess, just jump back in. So we had just finished with some rules for working with probabilities, things like disjoint union and the sum rule, and I'd like to point out that all of the stuff that we've just been learning about sets and logic, this all should help with probability as well, in the sense that events are just sets, right? So we have our sample space, that's a set, and the events are subsets of the sample space. And so all of the set operations, like union and intersection, they all work with events, and all of the rules that we know for working with unions and intersections, they all apply to events as well. Same thing with logic. So a set of events is exactly the same as a proposition, right? A function that's true on some atomic events and false on others, right? So an event is a set of atomic events, and that's the same as a proposition defined over atomic events. And so all of the logical rules that we have for working with propositions, they all apply to probability as well. So in particular, if you have a proof about the relationship between some propositions, right? Like maybe you prove that, the thing we proved about the lemma about the peanut butter and jelly in a couple of classes ago, right? So this, if you think of the propositions, peanut butter and jelly, as being events, things that could happen, like I could have peanut butter or not, and it might have some probability, then the logic that I proved, the theorem of logic that I proved, is a statement about the events that could happen in the world. And in particular, as we mentioned yesterday, implication is a relationship between the probabilities of compound events, right? If A implies B, that means that B is true in all worlds where A is, in all atomic events where A is. And so that means that the probability of B has to be at least as large as the probability of A, right? And you can, every result that you can prove in logic, you can make a corresponding statement in probability. So, for example, there's an example here about De Morgan's laws, right? So De Morgan's laws tell us about the relationship between this expression, not A and B, and this one, not A or not B. They say that they're the same proposition, and therefore if A and B, if these propositions, if we interpret them as events in a probability space, that means that the probability of this event has to be the same as the probability of that event. All right, so so here's an exercise that we can do. We're not going to hand this one in, but I think it's probably worth pausing for a minute or two to do this. So let's pause for just a few minutes. Feel free to ask questions about the exercise or anything else on Piazza. And when we come back, I'll work through the exercise so that you can compare your solution to mine. All right, so here we are back again. So let's work out the exercise. So we're describing a probability space where there's two events: the yes/no for the first question and yes/no for the second question. So we can draw that like this. Here is our sample space, right? And we have the first question and the second question, right? And so there's four possible regions, right? There's yes to the first, no to the second. There's yes to both. There's no to the first, yes to the second, and there's no to both. All right, and so that's our Venn diagram. And so we have some facts that we know from the question. So let's write out those facts. 67% of people respond yes to the first question. So yes to the first is regions A and B in the Venn diagram, right? And so we know this is true. We know this expression here is true by disjoint union, right? So A and B, these sets are disjoint. And so their union, which covers all of this first circle, is just the sum of their probabilities, right? And so the probability of region, right? So A is the probability of this region, B is the probability of that region, and together they total 67%. Same thing with the second question. We know that B plus C is equal to 0.9, right? So, you know, it's pretty clear that this street corner is probably somewhere near Carnegie Mellon, right? It's got to be in Pittsburgh for the love of the Steelers, and it's got to be near Carnegie Mellon for the love of computer science. All right, so the last thing that we have is that both questions here, right? That's B. Region B is B is the probability of answering yes to both questions, and that is 0.65 according to our givens. All right, and now all we have to do to answer, right, what we would like is the probability of finding a person who responds no to both. That's just D. And so what we can just solve for D with just some linear algebra. So let's go ahead and do that. There's a bunch of different ways you could do it, but let's start by, for example, adding together these first two equations, right? That gives us A plus, right, B appears in both, so we get 2B plus C is equal to 0.67 plus 9, that's 1.57, right? And then we know B is 0.65, so let's subtract that off. So A plus B plus C, we subtracted off one of the copies of B, and we subtract off 0.65, so that gives us, I guess, 0.92, right? And we know that A plus B plus C plus D is equal to 1, right? Because that's the entire sample space. And so that means if we subtract this guy here from this guy, that means that D is 0.08, right? So that's how to solve that question. And that's a pretty typical question of the sort we might ask you about these probability manipulation tools. All right. So a couple of things I should mention about probabilities. So one is that we've assumed so far that our set of atomic events, which we're writing capital S, we've assumed so far that that's finite. Everything sort of still works if you work with an infinite set of events, but you need to be careful, because there's a lot of crazy math and even some paradoxes that show up if you try to sum over an infinite set of events. If you're curious, you should look up the Borel-Kolmogorov paradox on Wikipedia. That is definitely not something you need to know for this course, but it's kind of a cool page, so have fun. But just as an example, just as an example of what can go wrong, the coordinate system, if you have probabilities over real numbers, the coordinate system that you use to express your vectors of real numbers, that can influence the probability calculations. And so, in particular, if you make a non-rigid change of coordinates, you can wind up, if you're not careful, changing the probabilities of events, even though you haven't, even though there's like a one-to-one mapping between them in the two coordinates. So that's kind of weird. So the advice is basically stay away from infinite sample sets if you can. If you can't, pretend that in fact all real numbers are just as discretized in a computer. Right? In other words, think of it as a finite but extraordinarily large sample space, and then you don't need to worry about anything. Then all of the rules sort of make sense. And in particular, the problem with that change of coordinates example was that when you did the transformation of coordinates, if it was non-rigid, it could map two previously distinct real numbers onto the same real number, and so. You know, that's a no-no, right? If you map one sample space onto another, if the mapping isn't one-to-one, then you shouldn't expect probabilities to be the same, right? Because, you know, the probabilities of two events that become one, those two events probabilities will add to become the probability of the other event. All right, so so that's one extension, is to infinite sample spaces. And if you're interested in that, there's plenty of courses at Carnegie Mellon that you can take. The general name of the topic is measure theory, and it's a lot of fun. Can kind of hurt your brain from time to time, but I consider that fun. So so enjoy. The other is the subjective versus objective view of probability. So the way that I typically think of probabilities, and the way that probably most people in computer science use them, is subjective. Like if I say the probability of event A is 0.63, that's my belief, and you know, somebody else might perfectly legitimately believe that the probability of that event is 0.72 instead. And so that's fine, as long as, and so what we're going to do for this course is we're going to essentially assume that everybody who's taking part in the conversation agrees on the probability space that we're using. In other words, they agree on what is the list of possible atomic events and what are their probabilities. And that's, that basically avoids a whole bunch of weird things that can happen when two people talk to each other who don't agree on the basic assumptions. And it's perfectly possible to develop the math to handle that situation, but that's beyond the scope of the course. So one could also imagine that there's some objective probability of an event. And that's fine, you can imagine that if you want, but it's not what we're going to be talking about here, right? Like we're going to be talking about our estimates of these probabilities, and all of these rules that we're giving you are rules that we use to manipulate our estimates of these probabilities to find out what we should estimate to be the probability of some other event that depends on these first ones. And if you're interested in figuring out what happens when people have different beliefs, game theory is a good place to start. All right, so that's the end of that set of lecture notes. Let's switch to the next set, which is the one on random variables. So these are all accessible from Piazza. So yeah, so let's get started from with random variables. So as before, we have our sample space, that's S, right? And let's imagine that we have a function that maps our sample space to real numbers. So that means for every atomic event, we're going to have a single real number. So for example, if we are taking a survey, a random variable could be the height of the next person who walks by. All right. And so that's a little bit different than the interpretation that a lot of people think of as a random variable, right? So, I mean, the simplest way of thinking of a random variable is it's a variable, it's something you don't know that's being set randomly, right? And you can map this interpretation, the one in the lecture notes, to that interpretation pretty easily. You just imagine that you know, there's some pseudo-random number generator in your computer or in the universe, right? And that's the possible values of that random number generator are your sample space S. And then based on that, you know, source of randomness, stuff happens in the world, and that's what we measure. And so the stuff that happens in the world is a function of all of the randomness that happens. And so we just think that there's some hidden you know, hidden source of randomness we don't observe, and we imagine that its bits are the atomic events, and then we observe some real valued function of it, right? Let's see. So these are real valued random variables. It's also perfectly possible to have random variables that are integers or booleans or you know, enums. Like for example, the eye color of the person who walks by next is a random variable. All right. So here's a picture that goes with random variables. So we list out our atomic events, right? Here I've got 26 of them. And what we've talked about in the last set of lecture notes are probability models. They just assign a probability to each one of these atomic events, right? And what we're talking about now is a random variable, which is a mapping from atomic events to real numbers or to anything else. Right? And so this this function here, from atomic event to random variable, from atomic event to its value, that's a random variable. And so a probability model and a random variable go together, right? If you typically, when you're reasoning about a random variable, there's some probability model that's implicit in the conversation. All right. So one of the things that we can do with random variables is use them to define events. So we could ask, for example, what is the probability that the next 5 cards that I draw form a straight flush, right? So I have a standard deck of 52 cards, I draw the top 5, I look at them and ask whether they form a particular poker hand, namely the straight flush. That probability is very low, but you can calculate it. The internet probably has multiple sites that will tell you what that number is. And so a lot of times when we're talking about random variables, the sample space is actually left implicit. We forget about the sort of, you know, underlying random number generator that we use to shuffle the deck, and we just talk about the random variables that we see, and we define our events in terms of those random variables. But it's important always to remember that there is a sample space underneath, and when we do probability calculations, what we're doing is reasoning about that sample space. All right. So for the same sample space, we could define many different random variables, and in fact, that's usually the case. So if our sample space is the set of possible people who could walk by as our next survey participant, we could define random variables for their height, their weight, their eye color, right? All sorts of different things, whether the second letter of their middle name is a vowel or not, right? Like, you know, all sorts of crazy functions that we could define that map the underlying sample space to some value. And so if we're in the situation where that I just described, where we are leaving the sample space implicit and just talking about the random variables, which is usually like what'll happen if you start reading a paper that talks about some random variables. They'll just list the random variables they're interested in, and they won't even mention what the underlying sample space is. So if you don't know what the sample space is, there's a nice recipe that lets you just construct the sample space, or maybe not the original sample space, but it's a sample space that's good enough to talk about these random variables. And what you do for that is you just list out every possible joint setting of all of your random variables, right? So if you have height, weight, and eye color, right, let's say height is a integer number of millimeters, weight is an integer number of ounces, and eye color is one of, let's say, 10 possible values, right? So then height could range from it's not going to be less than 0, and it's not going to be greater than 4 meters, right? So you have like some bounds on it. There's a finite number of possible. There's 4,001 possible numbers of millimeters between 0 and 4 meters. Same thing with the number of ounces between 0 and, let's say, 1,000 pounds. And I said as well that we're going to consider 10 distinct eye colors, right? So you just look at all possible joint settings of those, and that forms your sample space. And then the random variables are pretty clear, right? You just read off from each one of these atomic events what the value of that random variable is going to be. Okay, and then to each one of these atomic events you can assign a probability. We might not know ahead of time what it is, but we can write down just a real valued, a non-negative real number for each one of them, and we can place equations that constrain these and solve for their values. And that's the goal of reasoning about this probability model. In this particular probability model, the one where the atomic events are just settings for all of the random variables that we're interested in, that probability model is called the joint distribution of these random variables. So we can write down a joint distribution as a probability table. There's actually two ways to do it. So let's look at the first one first. So here is height as an integer number of inches. Here is eye color, let's say only 3 possibilities for now. And then at each, like for example, this cell, 0.2, says what is the probability of somebody being 5 foot 3 inches with blue eyes? Right? And so all of these numbers in this table are going to be non-negative, and they'll add to 1. And so here, this is a joint distribution over 2 random variables. You can equally well have 3 or 4, and then our table winds up being harder to write on a piece of paper, right? Because it's going to have 3 or 4 dimensions. So we'll have, let's say, rows, columns, and layers as a 3-dimensional table. If we have, let's say, height, weight, and eye color. And a table like this is often called a multidimensional array. It's also often called a tensor. And the dimensions, like the number of different random variables we have, those are called modes of the tensor. So a probability table, though, is a little bit more than just a plain matrix or tensor. It's a labeled matrix or tensor, right? So here, for example, we have 2 random variables, x and y. And here I've written x on the rows and y on the columns. Here I've written y on the rows and x on the columns. But these are actually the same, right? If you look at any given event, let's say the probability that y takes its first value and x takes its third value, that's 0.3 here, and it's 0.3 here, right? So they represent the same distribution, they're the same probability table. Whether we wrote x on the rows or columns is just an artifact of how we decided to write it down. And so that's important because it means that when somebody just gives you a matrix and tells you it's a probability table, you don't immediately know how to interpret it, right? And there are a lot of bugs in programs that come from somebody handing you a matrix and you not understanding whether it was the rows that are x and the columns that are y or vice versa. All right. So just briefly, another note about how to read a probability table. If you want the probability of a compound event, let's say the probability that x takes its first value, right? So there's two atomic events where that happens, right? Y could either be its first or its second value. And so the probability is just the sum of those. You just use the sum rule to read off the probability of compound events. Okay, so for multidimensional tables, it's kind of useful to be able to write them down on a 2D piece of paper. So what people will sometimes do is just essentially traverse all of the entries in some predefined order. If you're a MATLAB aficionado, this is what the colon operator does, right? Like A of colon takes your matrix and lists out all of its entries one after the other in a predefined order. You may also know this operation as vec of a matrix or of a tensor. And so here's an example. If we take a 3-mode tensor where the modes correspond to height, weight, and eye color, we can just list out. So here, the height is 5'3", the weight is 130 in all of these, and brown, blue, and green are the possible eye colors. And now we've incremented the weight to 131, and we go through brown, blue, and green. And then after we've incremented the weight through all of its possible values, we could increment the height to go to 5'4". Right, and this is only a small fraction of the table. There's lots of heights smaller or larger than 5'3". There's lots of weights smaller or larger than 130. And this is the same probability table as if we had written it as a 3-dimensional 3-mode tensor. It's just a different format. And so you might get a probability table in either one of these formats, and you should just be familiar with both so that you can read it no matter how somebody gives you one. All right. So I think now might be a good time to pause for we'll do a brief quiz. So because today is the Technical Opportunities Conference, instead of having the quiz be due immediately after the class period, we're going to give you until midnight tonight, 11:59 p.m. To fill it out. So I'm going to go ahead and make that public. All right. So you guys should all be able to see the assignment now on Canvas. It's got a link to Q&A to answer the questions. So I'm going to go ahead and start watching Piazza for questions, give you guys a few minutes to work on the quiz, and then we'll be back. All right, so we're back now. If you're still working on the quiz, feel free to pause the lecture and keep working. For those who are done, which it looks like there are a decent number of people who have finished, let's keep going with probability. So, if we have a joint distribution, meaning a distribution over several random variables, height, weight, eye color, we can ask for the distribution over just a subset of those variables. For example, just height and eye color. And so the second distribution is called a marginal of the first one. And figuring out the marginal, forming the table for the marginal is called marginalizing. So marginalizing given a probability table is actually straightforward. If we have let's say a 3-mode tensor, what we do is we just sum along one of the modes, right? So one of the modes corresponds to the variable we're marginalizing out, and so for every cell in the new distribution, we'll just sum together a bunch of cells in the original distribution. So for example, if we look at the table up here, for height versus eye color, this one. If we wanted to marginalize out eye color, we could just sum along this row, and so the probability of 5'3" is 0.8, the probability of 5'4" is 0.105, it looks like, right? And so you know, we're just summing along a row of a matrix or a column of a matrix or just along a mode of a tensor. And so, you know, with small tables, that's easy. With larger tables, it can be computationally pretty difficult. And so some of the things that we'll do with our rules of probability is figure out how to calculate the marginals without actually enumerating all of the possible values. Okay, another thing we can do with a table is to create a conditional distribution. So a conditional distribution means, let's say that we know for sure, so we start out with some probability table and then we find out for sure the value of one of the random variables. That's called observing it or conditioning on it. Then we know that all other possible values of that variable are no longer possible. And so what we'd like to do is ask, how does the probability distribution change given this extra knowledge? And so what we can do is we just scratch out all cells of our probability table that are incompatible with our new knowledge, and then renormalize so that it's still a probability distribution. So divide by the sum of the remaining entries. So for example, if we go back up to the table for height and eye color here, this one here, if we condition on height being 5'3", then we just take these three entries, 0.05, 0.02, 0.01, and divide them all by their sum, 0.08. And if you go back here, right, so here, 0.05 divided by 0.08 is 0.625, and so we just get these values that sum to 1, right? So it's worth talking a little bit about the notation that we use for conditional distributions. So if we have 4 random variables, x, y, z, and w, the expression p of xy given zw means the conditional distribution of these guys, the ones to the left of the conditioning bar, conditioned on or given these guys, z and w. We can for this here means a table, right? So there are 4 possible random variables here. For every value of z and w, we'll get a distribution over x and y, which means we'll get a probability for every setting of x and y, right? So for every possible setting of x, y, z, and w, there'll be a number that's the conditional probability of that setting of x and y given that setting of z and w. And we can, if we want to, fill in specific values of the random variables. So just like we can say p of x to mean the table for all values of p of x versus p of x equals 1 for the specific value, specific probability of the event x equals 1, which is an entry in that table. We can do the same thing. We can fill in values for x, y, z, and w. So we could ask for probability that x is true and y is false, given that z is 3 and w is 1. And we can fill in, for example, some of the random variables, but not others. So p of x, y given z equals 3, w equals 1. That's a two-dimensional table because we took a four-dimensional table and we fixed two indices, and that leaves two indices free to vary. So we're asking for all the possible probabilities of every setting of x and y given a specific setting of z and w. So that's a two-dimensional table indexed by x and y. And a mistake that people often make, a conditional probability distribution is a distribution over x and y for each setting of z and w, right? So if you ask here, for example, if you ask p of x, y given z equals 3 and w equals 1, that's a 2D table, and all of the entries in that table together sum to 1. Probabilities, conditional probability distributions do not sum to 1 over the conditioning variables, right? So we could ask for the probability that x is true and y is false given z and w. That's a table indexed by z and w, right? All possible values of those. And if you sum out z and w, you typically won't get 1. Or if you look at this table, right? This table is a four-dimensional table, and if you sum over the entire table, you also won't get 1, right? You'll get 1 for each slice of x and y, but then there's many possible values of z and w. And so each slice sums to 1, and the whole table is going to sum to more than 1. And so something that I see every year is students normalizing a probability table by dividing by the whole thing, even when it's a conditional probability table, and they'll get the wrong answer that way. So here, let's just make an example of a distribution over 3 Boolean variables. If we have a table, so what we want to do, right, is to make a table that lists all possible values of all of the variables together. So if there are m Boolean variables, you'll have 2 to the m elements. And so let's use the example where, let's use the format where we write down all of the values one after the other. So that means a table with 2 to the m rows, right? The values of the possible variables on the left and the probabilities on the right. And so here, right, is a Venn diagram of all of the possible values of A, B, and C, and we've written the probability of each one of these atomic events inside the corresponding region of the Venn diagram, and then we've written the same information up here in the table. And then we can use a joint distribution, right? So here's another table where there's 3 Boolean variables, so 8 possible rows. And we want to ask, for example, the probability in this table that the gender of the, let's say it's a survey participant, the gender is male. And so here, right, there are 4 rows that correspond to gender being male. These 4 probabilities, you'll sum them together and you will get that number there. Same thing if you want to know whether somebody is, what the probability is of somebody being rich, right? So here, there are also 4 rows that correspond to rich, but they are, alternating rows instead of a group of consecutive rows. But the same thing happens, you just sum all of them together and you get the probability of that event. And here, right, this is a joint event, and you can go through and look at, right, all of the rows where rich is true, right, that's these four, and then filter out the ones that are male to get the ones that are female, and you just add together those two, and you get that number. All right, so here's a, I'm not going to go over this exercise in class, but this is a good exercise for practice if you would like. So it tells you a particular recipe for building a probability table, right? So it says that there are 3 random variables, so it's a 3-mode tensor. The total number of entries is 2 times 3 times 5, right, which is 30. So there are 30 possible entries. And here is a formula that you can use to fill in the entries. It's some normalizing constant times x plus y plus z, and you can figure out what the normalizing constant is because you know that all of the probabilities have to sum to 1. And so the exercise is to build this probability table and answer some questions about the probabilities of events. So I encourage you to, you know, when you get a chance, give a try to this exercise. Again, you don't need to hand anything in for this. This is just for practice. All right, so let's move to the next set of lecture notes, which is on mean and variance. And these, again, are linked on Piazza and the lecture schedule post. Hopefully all of you have saved a link, saved a bookmark to this post, because obviously it's a useful one. All right, so given a random variable, there's a bunch of things we can ask about random variables. One of them that's very common is the mean, right? So the mean, also called the expected value, is basically just the average of what you're going to get, weighted by the probability, right? So it's the sum over all events x of the probability of the event x times the value of the random the event that our random variable takes the value x times the value x, right? So for example, if x is from 1 to 6, representing the roll of a fair die, its expected value is 3.5, which is equal to this expression, just the sum over all 6 values of the value times the probability of that value. An alternate notation for the mean is x bar. So we already mentioned a bar as negation in propositional logic, but unfortunately every notation is used for more than one thing. You know, it's just our job to warn you about the collisions we know about. So we'll typically use we'll use both of these, but we'll use e of x probably more often than x bar. All right, so if you have a random variable x, and if you have a deterministic function f, then f of x is another random variable, right? Because basically x is itself a function of the atomic event, right? So let's say, you know, the atomic event is a card that we draw from a deck. X is the value of the card from 1 for ace, 2 for 2, up to 13 for king. And f is the function that squares its argument, right? Then f of x is also a number, and it's also a function of which card we draw from the deck, right? So it's just, you compose f with this other function g that gave, I guess this other function is called x already. So you compose f with the function x that tells you your value of your random variable given the atomic event. And so in our fair die example, right, we can make a function x squared, and we can apply it to the value of the die roll. And so we can ask for what's the expected value of the square of the die roll. And the same formula applies. You just sum over all possible values, the probability of the event times the value of the random variable given that event, right? And it gives you this number. X squared is a special one. a special function. For the monomials, 1x, x squared, x cubed, and so forth, the expected value of those monomials is called a moment of our random variable. In particular, the mean is the first moment, e of x squared is the second, e of x cubed is the third, and so forth. And this is specifically what's called a non-central moment, and we'll get to central ones soon. All right, so expectations are really important to work with, and one of the most important rules for working with them is what's called linearity of expectation, which is basically that you can take expectation as an operation that you do on a random variable and pass it through any linear function, right? So if you have a random variable x, you can take a linear function of that, ax plus b, and the expected value of that linear function is just the linear function applied to the expected value of x. So you've taken the expectation from the outside, pushed it inward through the linear function, and gotten it to be just around your original random variable. And you can do the reverse as well, right? You can start from here and go to here. So for example, the expected value of 3 times our die roll is 3 times the expected value of our die roll. So when we're working with expectations, that's possibly the most common rule that we use to work with them. All right. So another common calculation from a random variable is its variance. That's defined to be its expected squared difference from the mean. So x bar here is the mean of our random variable. That's a constant. It's no longer a random variable. X minus x bar, that's a linear function of x, so that's a random variable. X minus x bar squared, again, it's a function of x, so it's a random variable. So you can take its expectation, and that expectation is defined to be the variance. The variance is an example of a central moment, and in particular, the moments of x minus the mean of x are called the central moments. Meaning, therefore, that the variance is the second central moment of our random variable. The third central moment is called the skew, and the fourth is called the kurtosis. You don't really need to know that, but you'll occasionally run across those in reading a paper or something. All right, so if we have a biased coin with probability p, and if we count heads as 1 and tails as 0, then if the probability of heads is p, the expected value of x is p, right? Because it's p times 1 plus 1 minus p times 0. Let's pause for a second, and if you haven't done it already, in some previous class, it would be good to verify this formula for yourself. So use the rules for calculating an expectation to calculate what is the expected value of x minus p squared. And have at it, and we'll be back in a couple of minutes. All right, so we're back again. So let's work out the answer to this question. So, right, so the our coin with probability p, its variance of x, that's equal to the expected value of x minus x bar squared, right? We already know that x bar is equal to p, the probability of heads, right? And so this expectation, we'll just erase that for now. We'll use that later. So let's write this out. This expectation is the sum over, well, instead of writing it as a sum, we'll just write, there are two possible values of x, 1 and 2. So it's 1 minus x bar, that's the heads, that happens with squared with probability p, and then 0 minus x bar squared with probability 1 minus p, right? And then we can just expand this out. X bar is p, so this is 1 minus p squared times p plus 0 minus p squared is just p squared times 1 minus p, right? And we can factor out a 1 minus p, so this is 1 minus p times, and then here we have a 1 minus p times p and plus p squared, right? And so this is p minus p squared plus p squared, that's just p, and so that's 1 minus p times p squared. Sorry, 1 minus p times p, right? Because the p squared cancels. And so that's the expression that we claimed for variance, and so it's good that we get, in fact, that expression. So I wanted to go back and mention one thing that I forgot to say, which is that the square root of the variance is called the standard deviation. That's a standard deviation is maybe a more interpretable quantity than variance, because if the value of a random variable is measured in some units, let's say centimeters, then the standard deviation is also measured in centimeters, whereas the variance is not. It's measured in centimeters squared, right? And so the standard deviation is in comparable units to the random variable itself. All right. So given the mean and variance, one of the things that is useful to be able to do is to control the mean and variance of your random variable. And so because of linearity of expectation, if your mean is mu, then the mean of x minus mu is 0, right? Because the expected value of x minus mu is the same as the expected value of x minus mu, which is the same as mu minus mu, which is the same as 0, right? Linearity of expectation also implies that if you divide something by its standard deviation, the resulting variance or standard deviation is 1. Again, the proof follows from linearity of expectations, and it's a good exercise if you haven't seen it before. So if you do this to a random variable, subtract its mean and divide by its variance, that's called standardizing, and it results in a random variable with 0 mean and unit variance, meaning variance 1. It's also called z-scoring for historical reasons that don't make that much sense. So, but the name persists. So if you hear about z-scoring, that means to standardize something. All right. So another thing that you can do with variances is you can do them for multiple random variables at a time. So in particular, let's start with just two random variables, column x and y. So you can get the variance of x and the variance of y, but you can also get what's called the covariance of x and y, which is the expected value of the product of the difference of x from its mean here with the difference of y from its mean. And the covariance measures how much large values of x, either positive or negative ones, tend to predict large values of y in the same direction for a positive covariance and in the opposite direction for a negative covariance. And if we standardize x and y before we measure their covariance, we get what's called the correlation. So the correlation is itself a covariance. It's the covariance of the standardized versions of x and y. So correlation is always in the range of plus minus 1. A correlation of 1 means that y is perfectly a linear function of x with a positive slope, and a correlation of minus 1 means that y is perfectly a linear function of x with a negative slope. So you have probably heard of covariance and correlation before, and you've probably also heard of a related concept called independence. It's important to remember that these are three distinct ideas that, covariance, correlation, and independence don't go hand in hand. So for example, let's see, two variables that are independent have zero correlation and also zero covariance. But the reverse is not true. You can have zero correlation without being independent. A good exercise would be to try and come up with a pair of random variables that have zero correlation but are independent, but are not independent. Right, so yeah, so come up with two random variables that are dependent, not independent, but whose correlation and covariance is zero. I'll give you a short second to think about it, but if you haven't seen it before, a hint is to try a uniform distribution on the perimeter of a circle and see what you get out of that. Excuse me. All right, so we talked about marginalizing and conditioning, and we can marginalize and conditionalize distributions that involve random variables, and we can ask for means and variances in those marginal and conditional distributions. So in particular, let's suppose we condition on some event A, then the distribution of x given A is going to be potentially different from just the distribution of x marginal of A. And so in the conditional distribution, x has a mean and variance, and those are called the conditional mean and the conditional variance. And we write them this way: the expectation of x given A and the variance of x given A. We can also condition on a different random variable. So, right, conditioning on an event, either happening or not happening, that's like conditioning on the two possible values of a binary random variable. You could condition on an integer valued random variable, for example, and then for each possible value of y, there would be a conditional distribution of x. X would have a conditional mean in that distribution, and the function that goes from the value of y to the conditional mean of x given that value of y, that's called the conditional mean of x given y. And so the conditional mean is it's a useful statistic. It lets us, for example, like it's a decent way to predict x if you know y, right? So if you're trying to minimize your squared error of your prediction, the best possible prediction of x is going to be the conditional mean of x given what you know, y. The last thing I want to mention is vector-valued random variables. So a vector-valued random variable is just a random variable that takes values in some vector space like R2. And therefore, each component of a vector-valued random variable is a real-valued random variable. And so when we ask for the expectation of a vector-valued random variable, we just take the expectation component-wise. And so, the expectation of x is the vector whose components are e of the first component of x, e of the second component of x, and so forth. And that's maybe straightforward because it's in fact the average of all of the vectors that you would get times the probability of getting that vector. What's maybe a little less straightforward is how we define the variance of the vector. So we define a new concept called a variance matrix. It's also sometimes called a variance covariance matrix because its entries are variances and covariances. But it's defined like this. It's defined to be the expected value of x minus x bar times x minus x bar transpose. So if x is a vector of length n, the variance matrix is going to be an n by n matrix. And if you think about it, the diagonal entries of the variance matrix are going to be the variances of the individual components of x, right? It's going to be like e of xi minus xi bar squared on the II diagonal element. And then the off-diagonal elements, you can again verify this for yourself, are the covariances between the different components of x. All right. So, yeah, I guess you're going to get lots of practice taking, like thinking about means and variances of vectors, and so it's a good concept to make sure you understand. I think we're getting close enough to the end of class time that it's not worth starting another set of lecture notes. So we'll stop here and we'll continue class on Monday. Just a reminder that there is a short problem set still out that is due, I believe it's due on Friday. Let me just look at Canvas to make sure. Assignments. Yeah, so the markup a proof assignment is due on Friday at midnight or 11:59 p.m. All right, I'll see you guys next lecture, which is Monday, and until then, happy machine learning.